Look at the chemical makeup of some of our most effective medicines, like penicillin, and you will find a specific architectural pattern at their core. These drugs rely on tiny, ring-shaped molecules that are packed with an intense amount of internal tension. Picture a thick wooden branch bending under physical pressure. That tension creates a massive reservoir of energy. Forced into this strained state, the molecule is extremely reactive. It wants to snap out of that tension and release its stored energy. When introduced to the human body, that energetic reactivity acts like an engine, driving the chemical reactions necessary to attack bacteria or fight off disease. Because this structural strain is so effective at driving cellular processes, our ability to develop new treatments relies heavily on whether we can successfully build these tiny, high-tension rings in the lab. But forcing a relaxed molecule into an unnatural, tightly wound shape requires tremendous effort. It is an energetic uphill battle. Historically, chemists solved this problem through brute force. They subjected their starting materials to severe, harsh conditions, primarily by blasting them with extreme heat. That heat generated the needed force, but it routinely destroyed the delicate parts of the molecule, specifically the vital side chains, known as functional groups, that branch off the main structure. Those side chains dictate how a drug interacts with human tissue. Destroying them during the manufacturing process severely limited the kinds of compounds chemists could produce, leaving researchers searching for a gentler way to build tension. Recently, a team of researchers at the University of Münster tackled this exact problem. They wanted a clean method to construct a highly strained house-shaped molecule, fittingly called a Housane. They began with a common, widely available group of hydrocarbons known as 1,4-dienes. This diagram shows the initial roadblock. Molecules follow the path of least resistance. When energized, they naturally avoid forming difficult, tense shapes, and instead splinter off into unwanted, chaotic side reactions. To stop this, the team used computer-based models to map out exactly where these messy chemical detours were occurring. With the map in hand, they systematically adjusted the original side chains of the starting materials. These tweaks acted as physical roadblocks, shutting down the alternative reactions until there was only one route left, the path straight to the Housane shape. By eliminating the natural escape routes, the scientists locked the molecules into a single trajectory. All they needed was the right burst of energy to push them across the finish line. Instead of turning up the heat, the scientists introduced a specialized additive called a photocatalyst and bathed the mixture in targeted blue light. The photocatalyst acts as a precise energy transfer device. It absorbs the incoming light rays and funnels that raw power directly into the hydrocarbon molecules. This diagram shows how that energy is utilized. The steady flow of light provides the exact momentum needed to scale that massive uphill energy barrier. The transferred energy physically forces the structure to cross the threshold and fold tightly into the compact, highly strained Housane ring. Because this transformation relies on cool, gentle light rather than destructive heat, the delicate side chains attached to the molecule survive the entire process intact. The researchers achieved the necessary structural tension without damaging the rest of the chemical architecture, demonstrating that precise light can safely replace brute force heat in organic synthesis. By proving we can safely fold these tense structures, this method increases the variety of complex molecules we are capable of building in a laboratory setting. For manufacturing, this provides a highly controlled, clean process that allows for the creation of chemical building blocks that were previously too difficult to isolate. It equips pharmaceutical companies with a more reliable toolkit to construct the highly specific components required for next-generation medications. This means researchers can pursue complex treatments that were previously considered too fragile or unstable to survive traditional chemical manufacturing. Replacing destructive heat with the precision of blue light allows researchers to build tension while keeping delicate side chains intact, offering a more reliable path to synthesizing the complex building blocks that modern medicine depends on.
That's all for this explainer. Keep asking questions. And as always, stay curious.